knowledge, strategy, tactics, quick wits. These are all skills required to master the game of chess, truly the peak of human intellect. But what if there was a greater summit, a mountain higher than Everest? Towering above all others is the vastly complex game of Pokémon. Okay, to be fair, chess still requires a great deal of intelligence to master, but let's not understate the complexity of Pokémon. You have hundreds of Pokémon with various types, stats, abilities, moves, and more that all come together to create a widely diverse game. So, with that complexity, I decided to dive headfirst and build an AI to master the art of Pokémon battles. Since the Pokémon Company clearly doesn't like money, there hasn't been an official battle simulator since service for Pokémon Battle Revolution shut down. So, the best alternative is Pokémon Showdown. Pokémon Showdown allows for several different battle formats from all generations. I didn't want to go through the trouble of building a team of my own, so I went with the Generation 7 random single battles, where random Pokémon are assigned to each team. To be clear, the assigned Pokémon aren't purely random. Instead, they're pulled from a pre-curated list of competitive ready Pokémon. So you won't be getting a Splash Magikarp while your opponent gets Judgment Arceus. The first hurdle was figuring out how to read and interact with the Pokémon Showdown API. I'm definitely not the first person to tackle this project, so I took a look at what other people did. Most solutions I found use a WebSocket to connect to the Pokémon Showdown servers, which absolutely is the most efficient method. But who needs efficiency? I want to watch my AI bully innocent children. I want to watch my AI valiantly duke it out in combat. For this project, I programmed everything in Python and used the Selenium library to interact with the web page. The way Selenium works is it launches a driver of your browser and programmatically interacts with the web page's source code. Selenium was originally designed to automate testing for web pages, but I'm sure the developers won't mind me appropriating it for a silly video game. To get a variety of interesting results, I set out to create 4 bots: a random choice bot, a strongest move bot, a deep Q learning neural network bot, more on that later, and a MinMax predictive bot. The first thing I needed to program was having the driver create a fresh account, then initiate the battle in the Gen 7 random singles format. From there, it was a matter of getting the Selenium driver to properly capture the battle information, the Pokemon available to the player, including its moves, stats, abilities, items, etc. And since this format hides your opponent's Pokemon information until they're revealed, including their moves, it can only capture a limited amount of information over time. To assist with the management of more complicated bots, each time the program encountered a new Pokemon, move, ability, or item, it would log the information it gathered and save it into its databank. The logging system found that there were at least 448 Pokemon in the Gen 7 random format, with 369 unique moves, 230 abilities, and 147 items. As you can imagine, this gradual collection of data was greatly preferred compared to manually building this database. The second bit of groundwork needed was logging the progress of the battle. Technically, I could have ignored this feature, but since I'm not always going to be watching the bot in progress, I'd like to be able to look back at the logs and see how the bot performed. This greatly helped in debugging in case something went wrong. But let me tell you, Pokemon has a lot of log messages. I mean a lot. Over the course of this project, I found over 300 unique log messages, where 100 of which virtually mean nothing to the bots. Alright, let's address the elephant in the room. Why did I choose Gen 7? See, since the second generation, Pokemon has added all sorts of features to the battle system, including new moves, forms, effects, and gimmicks. Up until Generation 8, the new gimmicks were fairly straightforward. In Gen 6, they added Mega Evolution, where Pokemon can get boosted stats and new abilities and type changes. However, in the meta for Mega Evolution, you pretty much just pop it as soon as possible. Only niche circumstances would warrant timing on Mega Evolution. Therefore, with this gimmick, I just set the bots to always enable Mega Evolution, if possible. In Gen 7, they added Z moves, which are just powerful one-use moves. While timing on its usage would be more advantageous, it's not imperative, so I just treated it as an additional move option. The real problem comes with Gen 8's Dynamax gimmick. When you Dynamax a Pokemon, its stats and moves are greatly boosted for 3 turns, and you only get to do this once per battle, so it's extremely important to time it right. Also, in single battles, it basically means that if you don't Dynamax at the same time as your opponent, you're pretty much guaranteed to lose 3 Pokemon. Gen 9's terrestrialization has a very similar timing problem, and I really couldn't be bothered to properly program this behavior. So, Gen 7 it is! I started out simple, and first built a bot that just takes all the available action options and randomly chooses one. That's it. Nothing special going on here. As you can probably imagine, this bot doesn't really perform well. After 100 battles, it won 18. With a final ELO of 1022. But hey, it got a max ELO of 1125, which is pretty middle of the road. So yeah, not that great. But that doesn't mean it wasn't useful. The majority of the data I gathered in the groundwork came from this guy. When I wasn't working on this project, I just left the random bot running to collect more data, making future parts of this project much easier to work with. For the next bot, I added a little bit of intelligence. Now, imagine you're 8 years old, playing Pokémon for the first time, knowing nothing about the deeper mechanics. Naturally, any move that does no damage is absolutely worthless to you. No stat buffs or status effects, only attacks. I call this the Little Timmy mode of play, or more appropriately, the Youngster Joey bot. The methodology for this bot is it calculates which move option will do the most damage. It does not use status moves, and it does not switch. While I mentioned that the Youngster Joey mode ignores the deeper mechanics, this bot at least takes into account same type attack bonus and boosts from abilities, weather, and items. This bot doesn't utilize the full extent of Pokemon's mechanics, but at least has more directed thought than the random bot. I was thoroughly surprised to see that it won 46% of its battles with a final ELO of 1145 and a max ELO of 1261. So it definitely started to reach some level of competitive play. I guess the bigger number, better trainer strategy has some merits. This bot was fun to watch and helped lay groundwork for the calculations that will be necessary for the remaining two bots. I pondered for a while on how to build a bot that utilizes some sort of neural network, since that's the buzzword that will grab attention. My first thought was to use the logs that I built up over time as the input data. The main problem with this would be the log translation. See, these logs are all written in human-readable terms, and if you're less familiar with programming, human-readable terms are not the easiest for programmatic systems to read. So my main problem with this approach was finding a generalized way to write these logs so that it would be consistent enough to extract data from. After putting in the painstaking work of translating all the logs, I conveniently remembered Q-learning. In short, Q-learning is a machine learning technique where an agent is rewarded or punished based on its actions, like a carrot and stick system. The idea is the agent doesn't fully know its medium and will do some trial and error to figure out what works. For example, imagine an agent is in a darkened maze filled with traps and must find the treasure within. Whenever the agent takes a step, it records whether that step led to a trap or a reward and remembers where that outcome was. This process restarts and repeats until the agent has gained confidence on its medium and solves the situation based on its stored memory. On the programming side, the reward system is driven by an equation written by the programmer, where the parameters of the equation can be adjusted as the developer wishes. Bringing this back to Pokemon, the idea is the battle agent has no idea what Pokemon is, so it takes observations every turn, then chooses one of the possible actions. After taking that action, it takes another observation and determines how quote-unquote good that action was. Now, since Pokemon is super complex, no single equation that I could come up with would properly solve the battle system. Therefore, instead of building a complex equation, we just substitute that with a neural network and let the computer do most of the work. Easy.
A few moments later.
Okay. I really didn't want to have to talk about the results of this bot. I really wish I could just pretend that it got amazing results, but no. After all that training, the DQN bot won 19 battles. 19! With a final ELO of 1038 and a max ELO of 1104. How do you do categorically worse than the bot that has no idea what it's doing? It's literally just taking random actions. And you did worse than that! How do you do that? That's okay. We'll just change up the parameters and retrain the network. I want to get this video out by the time of Scarlet and Violet's release, so I've got plenty of time, right? Let's see when they release. I wanted this bot to do really well, but the problem is the time sink of training it. I mean, this network alone trained on over 16,000 battles, and this wasn't my first attempt. Each change to the network or the parameters would require starting the training all over again. And you really don't see the results of the changes until you're already deep within the training. Each battle can take approximately 4 minutes, so you do the math on how long it'll take to retrain the network. One thought would be to try supervised learning, where the bot watches actions that I would take in battle and try to replicate that. But again, that would be another massive time sink. Still worth considering as a future extension to this project. The last bot built was by far the most complex. So, the way this algorithm works is I effectively wrote the logic of Pokemon, including move effects, abilities, and items, and assigned a reward system similar to the DQN. To be clear on the differences, the DQN bot learns the Pokemon battle logic over time, while this bot is pre-built with the knowledge. Just like the DQN, it takes in the initial conditions, but now it also takes in the potential actions of the player and the opponent, including switches. With each player-opponent paired action, it creates a node, representing the potential reality of both actions being taken. Then, for each node, it runs the Pokemon battle calculations to determine the potential outcome of said action, assigning a reward value based on how advantageous that result would be for the player. Once the calculations are done, it creates a new layer of nodes based on the potential actions for the following turn, continuing to make predictions. Once it has either run out of new possibilities or reached a certain calculation time limit, the algorithm takes each group of child nodes, averages their reward value together, then applies this average value to the parent node. This process continues until we reach the children of our initial node. We then group these nodes by the selected player action and average their values together. Whichever action has the highest average value will be our chosen action. The effective purpose of this algorithm is to predict the possibilities of future turns and find a path to the most optimal outcome. While not a completely accurate name, we'll call this bot the MinMax bot. After 10 hours of battling, the MinMax bot won a total of 42 battles out of 100, with the final ELO of, unfortunately, 1071. But it reached a max ELO of 1206. It is painfully clear that this bot performed worse than the youngster Joey bot. I will try my best to rationalize why this bot didn't surpass the others. Due to the sheer vastness of Pokemon mechanics, I couldn't feasibly program all the rules and interactions without losing my mind. I mean, the code I've written is already a massive mess. Let's just say I've gained a serious appreciation for the developers of Pokemon. Now, another limiting factor to this bot is the processing time. Ideally, the MinMax bot should be able to look several turns ahead to help determine the best outcome. But due to the time limit, it can reasonably only look 1 or 2 turns ahead most times. Furthermore, the longer the bot runs, the more bogged down the Selenium web scraper becomes, thereby increasing the time it takes to calculate, coming into direct conflict with the time limit. In the future, I plan to experiment more with this bot, maybe increasing its time limit to see what kinds of actions it would take. But that's for another time. Now, this project was definitely a time sink, though much easier to properly program compared to my last project. While there are definitely improvements to be made, I'm still quite satisfied with the work. While in the process of making this video, I took some time and also set up the bots to be able to challenge specific people. There may be a follow-up video, so please help spread the word about this video, if the feeling takes you. If you're interested in trying out the bots yourself, the full repository for this project is listed in the description. I'm always looking for ideas, so let me know in the comments ways you think this could be improved or other fun project ideas I could tackle. Also, if you're into the competitive Pokemon scene, let me know your favorite team or generation mechanics. See you in the next one!